It's a real pleasure to be here. And before I do anything else, I want to first show you where I come from. So this is Madison, Wisconsin. It's like this all year. If you're interested in pursuing graduate studies or a postdoc, it's a great place to live. So please send us email. Let me also thank first Professor Madison, who actually sent me the letter inviting me to be here. I'd like to thank the lecture committee for choosing me to be here and allowing me to present our work to you. I'm very grateful for that. I want to thank Professor Vigo. I will not pronounce your last name, Vigo, because I will mispronounce it, for spending a lot of time with me over the last 2 days. And a very special thanks to Professor Hasayer. He really is one of the giants of rheology. He's inspired generations of young people like myself to pursue work in this area. And I wouldn't be here if it wasn't for him. So thank you, Ole. And then I also want to thank all the faculty and students that have met with me over the last 2 days. I go on a lot of trips. I visit a lot of places. There are very few instances where I can say that every single meeting and every student that I met is extremely bright, full of ideas, and really motivating. That has been the case here at DTU, so it's been an extraordinary 2 days. Thank you very much for spending time with me. All right, so with that, let me get into the actual subject of my lecture. So we all know that self-assembly happens spontaneously, but it doesn't happen instantaneously. And we often find ourselves applying fields or shaking a beaker or applying ultrasound to obtain desirable outcomes. One of the things that I would like to do in my work is try to use rational theory and simulation to design self-assembly processes that lead to desirable outcomes. So we do that in the context of genomics, for example, where we try to manipulate DNA. We do it in the context of copolymers, where we try to motivate self-assembly. And we do it in the context of liquid crystals, where we try to guide the assembly of particles. There are many platforms under which you can try to investigate self-assembly. So to try to rationalize the work that we do in the group, we tend to divide the problem using the table that you see over here. So on the one hand, you have the nanoscale object that you're trying to assemble. In the simplest of cases, you can have spherical nanoparticles that you're trying to move in a system. In more complex cases, you can have flexible heterogeneous molecules like DNA, for example. Then at the other end of the spectrum, you have the medium in which you're trying to accomplish the assembly. So in the simplest of cases, the assembly can take place in water. In my field, water is a very simple continuum solvent. You can have more complex cases where you have solvents that have structure, or solvents that are inhomogeneous. And finally, you have the fields that you try to use to drive the assembly. Those fields can be flow fields, magnetic fields, nematic fields, or surface fields. So what I will do this afternoon is actually illustrate some of our ideas in the context of 2 examples. In the first one, we'll have very simple spherical particles and then an inhomogeneous solvent. In the second case, we'll have more complex particles and then a structure solvent and the application of fields. What I've tried to do with this lecture, I was warned that this was going to be a general audience. And when you have a general audience, you can do 2 things. Either water down everything and make it super simple, or put something that perhaps everyone would like. I went with the second option. We'll see how well it works. All right, so if you're falling asleep at the beginning, then at the end, wake up, because it might be something for you. All right. So we'll start with this example in which we have simple particles, inhomogeneous system, and surface fields. Now, we're in an engineering department, so much of the work that we do is driven by applications. The first application comes from the work of semiconductor fabrication. What you see here is a picture of a semiconductor, your typical Pentium chip. To me, this is truly one of the marvels of the modern world. The fact that you can place all of these tiny circuits at a very high density, reproducibly, at the tune of thousands of them per hour without making a single mistake is simply extraordinary. And one of the workhorses that has allowed us to create this incredible structure is the lithography process. So what you do in lithography, for those of you who are not familiar with these ideas, is you take a silicon wafer, then you coat it with a polymer film. And the role of this polymer film is actually to provide protection of the silicon for subsequent etching. So what you do is you create a drawing or a pattern on the polymer film that's shown in red over here. And then once you expose this to an acid, for example, you can actually etch away the silicon and deposit metals. So that's what becomes the circuit that you see over here. Now, one problem is that as the semiconductor industry tries to go to faster speeds and smaller microprocessors, the separation between these lines that you see over here is becoming smaller and smaller. And when you do that, one of the things that you find is that materials that in the bulk have some behaviors, when you go to these very small dimensions, behave very differently. So in this picture, you have walls created with PMMA, it's polymethyl methacrylate, so it's a polymer that at room temperature should be a glass, very, very stiff. You take the same polymer and you make it a thin wall, and you see that it actually bends, it flows, and it cracks. So this would be useless for lithography processes. Turns out that this collapse of photoresist structures is becoming one of the major roadblocks for this industry to go to smaller devices and higher densities. So this industry really needs to overcome this problem and come up with alternatives. Otherwise, we're stuck with the current speeds. So one idea would be to use block copolymers to create structures like the ones that you see over here. So block copolymers are these polymeric molecules that have two blocks. One is always blue and the other one is always red. And blue likes blue and red likes red. And as a result of that, when you go to sufficiently low temperatures, they microphase separate and form some very interesting order structures. The characteristic dimensions of these order structures tend to be in the tens of nanometers, which is exactly the length scale that we need for device fabrication. So our idea was to try to combine the benefits of available tools in the lithography industry with the attractive aspects of self-assembly to create order structures. So the way we would do that is as follows. We take a surface, we create a pattern on the surface using X-rays, for example. We can create lines of hydrophilic and hydrophobic. We can then spin coat the diblock copolymer. And then as we lower the temperature, these would like to phase separate. And if we do everything correctly, the block copolymer that you see over here would follow the instructions that are given to it by the surface. All right, so that's the general idea. So what you see here is then a simulation of a diblock copolymer in the box. So when it is warm, it is completely disordered, it's homogeneous. As you lower the temperature of the system, it spontaneously self-assembles into a lamellar structure if the two blocks have the same dimensions. And you see that red goes with red, blue goes with blue, and you form the lamella that you wanted to see over here. All right? Now, what you would like to do is take this lamellar structure and follow the instructions that you give it on the surface. And what is interesting is that most of the time, you find out that the polymer does not want to follow the orders that are given by the surface. In this example, you see that these lamella start to go up from the surface, and then all of a sudden they turn. And once they turn, you cannot use this for lithography because at the top, you have only one color, you have no pattern. In the bulk, if you take this material over here and you look at the phase behavior, it can only form two phases. It's either disorder or it's lamella. So just two phases. When you go to thin films on a patterned surface, you can actually form many, many different phases. Again, it is the same material, but the moment you go to small dimensions, it behaves differently. What you see here is an example of some of the phases that you can form. So the important variables in here are L sub s, which is the characteristic dimensions of the pattern that you have on the surface. L sub 0 is the characteristic dimension of the diblock copolymer. When Ls is equal to L naught, everything is commensurate, and then you have perfect lamella. This is an example of one of the phase diagrams that you could have. So what you see here is the thickness of the film in units of L naught, the characteristic period, as a function of the mismatch between the pattern on the surface and the characteristic period. of the die block copolymer, all right? We like to have green phases, which are lamella standing up. As soon as you deviate from P equals to 1, you start to see purple, yellow, and red, which are different phases that, again, you cannot use for fabrication. Now, we started this work about 10 or 12 years ago. And at the time, there was some competing predictions that indicated that this green domain that you see over here was actually extremely small, very, very small. So small that you couldn't use this for any practical applications. Generating these diagrams at the time was incredibly painful. Each of the points that you see over here, which was generated using lattice simulations of block copolymers, took about 6 months of computer times. And the lines that you see here are a very approximate theory that we used to delineate the phase behavior. So we couldn't really trust our predictions very, very much. And there was this other competing technology. And our experimental collaborators kept trying and trying and trying to generate lamella, and it wasn't working. And right about the time when we were ready to give up with this process, my colleague Paul Neely came through with these amazing experiments. And he was able to show that you could indeed guide the assembly of die block copolymers into these perfectly ordered structures using patterns on the surface. So what you see here is polystyrene PMMA, so a die block copolymer. It is symmetric. It forms lamella on a homogeneous surface, but the lamella are standing up. So that's why you see this fingerprint pattern. All right? So you're looking at the lamella top down. The moment you self-assemble exactly the same material on a surface that has lines on it, you get these beautiful structures. So this was a surprise to us for 2 reasons. The first one was that you could do it at all. We were ready to give up on this process. More importantly, you see that you don't have a single defect, not one mistake, over relatively large areas. And that was a surprise. We thought it would work, but not as well. So and as soon as we generated these results, we immediately went to our industrial sponsors. Intel was paying for this work at the time. And we told them, that's it. We solved the lithography problem. We need more money from you. And they laughed at us and they said, that's very cute, Juan, but it's really not very useful. What you really need to be able to show with this approach is that you can actually create these complicated structures, which is what you see in the circuits. You have bends, you have corners, you have interconnects between different layers. You need to be able to do all of these things with a block copolymer. So we went back to the laboratory and we tried to start to predict what would happen when you have these patterns on the surface. It became clear very quickly that this approach that we were using, where each calculation was taking 6 months of computer time, was intractable. So we had to come up with a different way of doing things. Eventually, what we ended up settling is the model that you see here. So I have 120 slides, but only I only have 2 slides with equations, and they're very important, so please bear with me. I think I need to explain them for the talk to be understandable. All right, so this is the model that we're going to be using then. It has an intramolecular contribution that tells you what is the connectivity of the atoms in your molecule. All right, so again, we have blue and we have red. And then we have an intermolecular contribution that tells you how the blue interacts with blue and how the blue interacts with red. All right? The parameters that enter the model are this chi parameter, which one can measure, and this kappa parameter, which is the compressibility of the system, and you can also measure that. Phi I and phi B are the volume fractions, or the local concentrations of A and B, and they depend on the position in the system. So with this approach, you can actually describe an inhomogeneous system. All right? Much of what we know about block copolymer behavior has come from this equation that you see over here. In many ways, it is the hydrogen atom of polymer physics, and this will be the Schrödinger equation of polymer physics. Everything that we need to know about polymers is built in here, and the problem that we have is one of solving this equation. We know what to put in it. Solving it is actually very complicated. So the traditional way of solving these equations has been to use what people call self-consistent field theory. So what they do is really very simple. They say that a polymer molecule can be represented as a random walk or a diffusion process in the field created by all the other molecules. So you guess a field, you solve a random walk in the fields, you see if they match. If they don't, you guess again, and you do it many times. The problem with this approach is that you don't have any fluctuations. And unless your guess is actually pretty good, you never converge to the correct answer, especially if you're working in 3 dimensions. Now, if you think about it, the problem that we're working on has characteristic dimensions on the length of 10 nanometers, and the film thicknesses are 20 nanometers. So fluctuations are extremely important, and you need to take those into account. So what we've done is introduce a series of methods that actually allow you to solve exactly the same Hamiltonian, but using particles, including fluctuations, and without including the fields in the system. All right. The model that we use is the same. The method is a lot more effective. So just to give you an idea of how that works, what you do is, instead of having those equations, you have millions of particles in a simulation box. You can discretize the system into small cubic elements, and then you can choose molecules at random, propose random displacements of these molecules, and then calculate the changes to the local composition, put that in the Hamiltonian, and accept or reject according to probability criteria that make sure that you sample the canonical distribution of configurations. All right. Now, the advantage of this approach is we can benefit from 20 or 30 years of algorithm development in the area of Monte Carlo or Brownian dynamic simulations, and get this to work and to converge very quickly. All right? So now, this is how it works. So whereas before we had a tiny little piece of material using lattice simulations, just 2 lamella, right? Those simulations were tiny. Now we can go to these very large domains. We start with a disordered system. In green, you see the interface between red and blue. You see the stripes at the bottom. And then you see that as you lower the temperature, the system self-assembles into these lamella that follow the pattern on the surface. At the beginning, you have defects. But as time proceeds, you see that these defects disappear, and eventually you have perfect registration between the stripes on the surface and the lamella. And if you were paying attention, you also see that throughout the entire process, the interface between the 2 blocks is actually pretty rough. Those are these fluctuations that I was telling you about. These fluctuations will determine what is the roughness of these interfaces. And that roughness will become a critical parameter when we actually design fabrication processes. All right. So using this approach, then, we set out to investigate whether you create corners. Very quickly became clear that you couldn't do it with pure block copolymers. You had to use blends, for example. So in this example, we have a blend of 40% homopolymer, so just red, and then 60% block copolymer, blue and red. What the calculations taught us is that to create these corners that you see over here, you had to mix them in exactly this proportion. And the way the process works is as follows. To relieve the stress that arises in the corners of these patterns, the copolymer recruits homopolymer from the straight segments to the corner. So you see that the concentration is high over here, it is low over here, but the stress is uniform, and you can create structures without defects. Using these calculations, then, we set out to explore all of the different combinations that would arise in a semiconductor device. This industry told us that we had to generate spots, T-junctions, jogs, bends, periodic lines. And then using a combination of theory and experiments, we were able to generate all of them. So now you see that the copolymer can give you the corners, the lines, the T-junctions, the jogs, and the spots. So this really works. And we think that one of the first applications that might be coming next year would be in the area of memory devices. So hard disks for very high density storage, terabyte disks. The way it's going to work is as follows. This is work that we're doing with Hitachi. Currently, your hard drives consist of a uniform magnetic film which you pattern, right? And you create magnetization in local domains. The problem is that because the magnetic film is uniform, those domains, for them to be stable, have to be pretty large. In order to have a higher density, one thing that you could do is create tiny little spots, as you see over here, all of them isolated with polymer in between. If you want to have a hard disk, then, that gives you a terabyte storage, in order to have 1 terabyte per inch square, the spots that you see over here would have to have a density of 27 nanometers. All right, so the separation between them has to be 27 nanometers. In principle, you could create one of these devices using an electron beam. Now, the problem with that is that the process is very, very slow. It would take about 6 months to create one hard drive. And the real big problem is that the stability of these instruments is actually about just 2 weeks. So in industry, I didn't know this before I started this work, they have something called the mean time to failure, or MTF. This is how long the instrument is stable before it breaks down. And for these fancy E-beam systems, it's about 2 weeks. So this is really impossible. Now, once you create one of these masters, then you're in business, because once you have one, you can actually reproduce it ad nauseum using what is called step and flash lithography, where they just take a mold and they just copy it. All right, and this is an established technology, and there's companies that can do that. So the problem then becomes that of creating the master that you see over here. How do you do that? Okay, one idea was what if instead of patterning all of the holes on the surface, we actually only pattern 1/4 of the holes? Then we can do it much faster. And what if instead of patterning the holes at a pitch of 27 nanometers, we make them bigger? And we do it very quickly, we're very sloppy. And then we use the block copolymer to fix all of the mistakes that we made on the surface. So we went to the drawing board, and then using theory and simulations, we identified what were the dimensions over which we could work, what were the molecular weights that we needed, what were the interactions that we needed between the surface and the materials. These are cross-sections of what you get for different situations. And what you find is that in many cases, the domains that you form are actually not completely straight, which is what you need for lithography. They actually form these hourglass patterns. Sometimes they don't go all the way to the bottom. Sometimes you don't have anything in the bottom. So what you want to have is what you see over here, just straight domains that go all the way through. So you find those conditions, you go to the lab, and this is what you find. These are the patterns created by E-beam on a silicon wafer, right? So this is done using the best instruments at Hitachi in Japan. And you see that when you go to 27 nanometers, even if you're extremely careful, the patterns that you create on the surface are very, very bad. They're dirty, they're full of mistakes. You could not use this to store data. Now, you spin coat the block copolymer on the surface, and this is what it does. You see that all of this noise that you have on the surface is gone away. It's the beauty of thermodynamics. It is these interfacial forces that are cleaning all of these interfaces and giving you these perfect patterns that you see over here. What about this second idea of patterning every 1/4 of the spots and make them bigger so that it's faster to fabricate? That's shown here. So this is the silicon wafer. You see now that the holes are bigger and that you only have 1/4 of them. You put the copolymer on top, you fill in the holes, and you make them smaller. So this actually works. We're very excited about this work. It was going great with Hitachi. And then all of a sudden, Hitachi said, you know what? We don't need spots anymore. Instead of spots, we need lines. So what we're going to do is fabricate lines and then chop them up and form little squares. And it turns out that that becomes a lot better for fabrication. That was great for us as theorists because we became relevant all of a sudden. Up to this point, we were, competing with the experiments. My experimental colleague, Paul Neal, is simply brilliant. He's very, very good at what he does. So he can do things very quickly. We didn't know anything about stripes. So we started to do the same thing that we had done with the spheres, but on stripes. So we only want to pattern one stripe for every 2 blocks. So we're interpolating, just as we did before, half of the lines as opposed to all of the lines. The parameters become the interactions of the stripes with the blocks, and then the mismatch between LS and L0 and the width of the stripes. So very quickly, because these methods work so well, we started to explore all of phase space. And this was great. We found out that no matter what you do to these systems, all combinations of molecular weights, energies of interaction, surfaces, etc., you can only form 5 morphologies. Only 5. They're shown here. So these are top-down images. So you're looking at it from the top. And these are cross-sections. You can form horizontal lamella, so they're lying down. Vertical lamella, those are the ones that you want. Mixed lamella, that's what they do. Dots or checkerboard patterns. From the top, the only one you like is these ones. These ones are useless. Subsequently, the experiments were performed in a combinatorial manner, and that's what they found. When we saw this, we were very excited because it became clear to us that you had horizontal lamella, you had vertical lamella, and you had dots. Now, our experimental colleagues were very skeptical about these predictions that you see over here. They claimed that what we're seeing were not dots, it was something much more interesting than dots. But we're pretty sure about these predictions. Now, it takes a trained eye to actually be able to say that this is the same as that. But finally, a few months ago, they were able to perform experiments at Hitachi where they ran cross-sections of these very thin films. And actually, we were able to see that you do have the structures that you predict in the model. In this example, you see vertical lamella. You see that they bend a little bit. That's what you see in the calculations. These are the dot morphologies, where you have these blue domains over here, these blue domains over here, and eventually these red domains over here. So the agreement is really very, very good. And what it shows is that we have a tool that you can use to really predict how these systems behave and to design processes. Now, one big surprise to us is summarized in this overhead. What you see here is a phase diagram for the morphologies that arise for this particular case. And this is just one example of many. This is the interaction of the background material with one of the blocks. This is the interaction of the stripes with the other one of the blocks. The squares here show you lamella morphology. Those are the ones that you want. The diamonds show you metastable dots or equilibrium dots. Now, if you run a simulation or you do an experiment with these parameters, you find that in here you get dots, in here you get lamella. The lamellar domain is actually very, very small. But yet, that's the one that you want to use for fabrication. If, however, you do thermodynamic calculations and you calculate precisely what is the phase line or the phase boundary between the dots and the lamella, you find that the phase boundary is actually all the way up here, right? So if the experiments were going to equilibrium or the calculations were going to equilibrium, all of this region should consist of lamella. And yet you find dots. What this is telling you is that these structures are actually metastable. Right? And that presented a major problem for us. For years, for 10 years, we've been telling this industry, you should use self-assembly because it is all driven by thermodynamics. And all of a sudden, once we become good enough and we can actually calculate the thermodynamics, we find that it's not thermodynamics, it's dynamics, and it is kinetics. So now we need to go back to the drawing board and refine these models so we can actually predict thermodynamics and dynamics. Now, the challenge then becomes one of describing the dynamics of polymeric liquids. So this is an area that was actually pioneered by Ole Hasager's advisor and then by Ole Hasager. The problem that we have is that in the models that I was showing you before, chains, as they move in the system, can cross each other. When you do that, that gives rise to dynamics that are actually in disagreement with the experiment. Real polymer chains exhibit entanglements, look like a ball of spaghetti, right? And chains have to follow certain paths. So what we've done is create models that allow you to describe those dynamics. We've validated those models by comparing to the best experimental data in the world. That's, of course, the data coming from DTU. These are the so-called elastic and loss modulus of the material. This is for polyethylene as a function of frequency. And you see that the agreement between experiment and simulation is quantitative. So this is telling us now that we can describe the dynamics of the system and start to predict non-equilibrium behavior. Now, what do we care? The memory industry, the hard disk industry, is going to be using these methods starting next year. So this is a done deal. Your hard drives will be created using this technology. What we really want now is Intel and AMD to adopt this technology also. And the sticking point for them to adopt this technology has been the formation of defects. See, when you're making a circuit, you cannot have a single mistake in a 9-inch wafer. If you make one mistake, you're toast. So this industry has been telling us for years, just prove that this process that you propose doesn't create a single defect. And we cannot do that. We cannot do that because you need to find one defect in a 9-inch wafer. It's impossible. How do you do that with an AFM or an STM? So the idea of one of our students was, why don't we use theory to predict the defect? Maybe they will buy that. They will. They're not that clever. Yeah, we can trick them. So using this dynamic method, then, we evolved the system in real time. We compare it to an experiment. You see that the defects that arise as a function of time, here in hours, here in Monte Carlo steps, are more or less the same. Once we form some of these defects, we can trap them. We can calculate their free energies. And it turns out that the probability of forming a defect is proportional to the exponential of the free energy. And this is an exact equation. So this prediction should be reasonable. When you do that, you find that for the most common types of defects that you find in your experiments or your simulations, the probability of forming a defect ranges from 10 to the minus 11 to 10 to the minus 237. So thermodynamically, and even kinetically, because these are dynamic calculations, it is impossible to form defects in this system. You have no idea how much trust this industry has placed in this equation. You know, they say that when you're a theoretician, nobody believes in your work except yourself. And when you're an experimentalist, it's the other way. Everybody believes in your work except yourself. So we're theoreticians. So on the basis of these numbers, this approach is now in the semiconductor industry roadmap, and they're going to start investigating it to create circuits. So this has been a successful story for us. All right, let me now switch gears a little bit and tell you about a very different application. So for those of you interested in biology, for example, this might be a little bit more relevant. So now we have simple particles, a highly structured solvent, and various types of fields, surface fields, nematic fields, and electric fields. This has to do with liquid crystals. We like to create biosensors that are based on the structure of liquid crystals. For those of you who are not familiar with liquid crystals, they're these elongated molecules that at high temperatures can form isotropic disordered phases. At lower temperatures, they can form slightly ordered phases that are still liquid, they flow, but they have directional order. And then at lower temperatures, they can form smectic phases. So these are, of course, the materials that you see on your computer screens. Traditionally, they've been used in the electronics industry, always, always, always in the absence of water. We want to do just the opposite, use them with water at interfaces. One of the first applications that we pursued in this area is illustrated here. So this was the first prototype of a biosensor that we created. So you have this surface here. The surface is rough. You have these grooves that go in that direction. And the surface is decorated with these red molecules that bind specific antibiotic or specific proteins. If you coat a liquid crystal in the system, the order is going to follow the grooves that you see over here. So when you look at it through a microscope and cross polars, the image that you get is here. It's completely black. The moment you bind a few antibodies to these red sites, depending on the concentration, you actually start to create these defects. So the optical images become what you see over here, where these lines are defects. And I'll explain what a defect is in a moment. So what these liquid crystals are doing for you is they're acting as reporters of interfacial events. All you need is a couple of molecules binding at the surface. That's a nanometer event. And the liquid crystal will amplify it over micron to millimeter length scales. All right? This has been used with proteins and viruses. Right now, the Department of Agriculture is using it to detect West Nile virus. So this actually works. But it's pretty awkward, because if you think about it, you can only use it when you suspect that you have a virus. If I think there's a virus, I bring out my surface, I pour the liquid crystal, I see if it changes color. It's not a continuous sensor. We would like to have something that continuously checks for viruses. So we're doing that in the context of two platforms. In the first one, we have nanoparticles suspended in a liquid crystal. In the second one, we have liquid crystals surrounded or trapped in a nanoparticle. Let me show you a couple of results for these two platforms. The way a sensor with nanoparticles will work is as follows. You can actually control the orientation of liquid crystal molecules at the surface of the particles. That orientation is extremely sensitive, exquisitely sensitive to the chemistry of the system. So by simply exposing these particles to whatever toxic agent you're trying to detect, you can actually change that orientation for perpendicular to parallel. And you can use that to drive the assembly of particles from that to that or vice versa. All right? The reason that happens is because you have defects in the system that the liquid crystal wants to minimize. So let's introduce then the concept of a defect. Let's assume that you have this spherical particle swimming in a liquid crystal. And let's assume that these molecules want to stand up on the surface of the nanoparticle. Let's also assume that nearby you have this flat surface and the molecules want to be flat at that surface. So now these molecules want to go that way. These ones want to go that way. And then at the place where these two orientations meet, you have no order. The liquid crystal doesn't know what to do. You have a defect. In 2 dimensions, you have a point defect. In 3 dimensions, you have a line defect. You have what we call a Saturn ring defect. So if you go to a laboratory and you look at a liquid crystal around a gold colloid, that's what you find. That's a gold particle in a liquid crystal, and there's your Saturn ring defect. These Saturn rings, they store a lot of energy, so the system doesn't want to have them. So what that does is when you have many of these particles, they actually attract each other in an effort to minimize the area of the defects. And those forces can be extraordinarily large. All right? Now, all of what we know about defects in liquid crystals, or most of it, comes with studies with very large particles, microns. And most of the time, we don't use particles, we use drops of liquid in the liquid crystal. So whatever happens when you go to hard particles and the nanoscale is really unknown. Now, this is an experimental movie from some collaborators showing you what happens when you have drops of a liquid in a liquid crystal. So the light gray over here is this 5Cb liquid crystal. Again, this is the fruit fly of liquid crystals. That's what everybody uses. And then the dark spots are silicon oil, so very simple oil. They're immiscible. This is an emulsion. If these were normal fluids and you shook it, eventually you will form 2 phases, dark and light, 2 homogeneous phases. But in a liquid crystal, look at what happens. Somehow, the oil forms these tiny droplets, and then they form chains. Well, the reason you do that is because you have defects separating all of these particles. Now, the amazing thing is that the distance between each of these droplets is exactly the same for all of them, almost to a nanometer. None of them are touching. The size of all the particles is exactly the same. And if we wait long enough, the separation between all of these lines is exactly the same. So this self-assembly is now driven by the nematic field of the liquid crystal. Now remember, these are drops. These are not nanoparticles. And they're very big. They measure 2 microns. What happens if we go to smaller length scales? So we're going to use multiscale modeling. We're going to work at all of these levels. I will show you results using just a continuum approach. Now, just one more equation. It's very important. All right. All right. Now, no. Look, there's nothing bad about these equations. It's just, look. It's just a free energy. You want to minimize free energy. All right? The free energy has 3 contributions. Enthalpy, right? It's here. Elastic energy. The liquid crystal doesn't want to be deformed. So you penalize the deformation. Right? You penalize it using mechanical constants. And finally, and the only reason I'm showing you these equations, you have a surface energy. This expression over here tells you what is the orientation of the liquid crystal at the surface of the particle. All right? You cannot change any of the parameters in this theory. These are properties of the material, and people measure them. The only thing that we can control is W. We can control the chemistry of the nanoparticle and control the orientation of the liquid crystal at the surface of the particle. All right, so that's the variable that we should be thinking about when we design these systems. All right, now we had not appreciated this surface energy over here when we started this work. Everybody in this field assumes that W is infinite, meaning that the orientation of the surface of a particle is fixed. It's either standing up or lying down, and nothing in between. And that's what everybody has done for many, many years. So we did the same thing. We started to calculate what happens when you have many particles. So you have two Saturn rings. The particles start to attract each other. They merge. They minimize the area of the defects, and that's more favorable. And when you go from the two particles being separated to being, for example, in a dimer, you gain about 100 KT. That's huge. It's an enormous energy. And this is coming just from the liquid crystal, not from any direct interaction between the particles. All right? If you place these particles near channels, for example, you can actually use these to separate particles of different sizes. You see that in going from that to that, you gain 1,000 KT. So when these predictions first came up, they were very intriguing. A number of people tried to verify this work using laser tweezers or optical tweezers. And sure enough, the experimental data suggested that when you go from isolated particles to these arrays that you see over here, you gain about 3,000 KT. Right? So this confirms some of the things that we were saying. We were not very happy. On the one hand, it was nice that the theory and the experiments were agreeing with each other. But then on the other hand, these energies here make this approach that we were proposing useless. Because what it really means is that the moment two particles touch each other, no matter what you do, the energy is so large that this is irreversible. So it becomes very difficult to create organized structures. The system does whatever it wants. And then we realize, wait a moment, everything that we're doing here has to do with infinite anchoring energies. But the moment you start to change that W parameter, you can actually control that energy very, very sensitively, provided you have nanoparticles in the system. So what you see here is the binding energy of this particle as a function of the diameter and as a function of the anchoring energy. And you see that whereas we used to have hundreds of KT, the moment you actually reduce this number, you can go to tens of KT, maybe even just a few KT, right? This is where we want to be. We then did experiments to try to confirm that, and sure enough, what you find is shown here. If you go to small nanoparticles now that measure just 150 nanometers in this case, you see that they come together, they separate, they come together. The predictions indicated that this potential of mean force was going to be about 5 KT. In the experiment, we get about 4 KT. So again, this seems to work. Now what this means now is that we can actually control reversibly the assembly and disassembly of these particles. Now the interesting thing is when you put many of them in a liquid crystal, you can form gels. So in the isotropic phase, you form a loosely defined network. You lower the temperature from 37 Celsius to 35 Celsius. You go from isotropic to nematic. This is a liquid. This is a hard gel. Here you see the modulus of the system, the elastic modulus, G prime, and you see that you go from liquid-like to solid-like, and this is reversible. If you were doing this with bigger particles, that wouldn't happen. It's always irreversible. This is reversible, and now the next step is to decorate these particles with receptors to specific toxic agents or antigens and use this as a sensor. All right? Now, the last thing that I wanted to show you is, let's assume for a moment that in designing these particles, we look at just one of these spherical domains over here, and we see how this spherical domain of liquid crystal interacts with the surrounding interface. All right? So this is what we've done here. You take this spherical domain, you encapsulate the liquid crystal using a polymer, using a multi-electrolyte deposition, polyelectrolyte deposition process. And then what's going to happen if you do that is as surfactant molecules or molecules that you're trying to detect diffuse through the polymer layer to the liquid crystal, they will change the shape of the defects that you have inside of the droplet. In the absence of any surfactant, the defects are going to be at the poles, right? The orientation of the liquid crystal is going to follow these lines. So the defects are here and here. As the surfactant starts to diffuse through this layer, it changes the orientation at the interface, and the shape of these lines goes from a basketball to what you see over here, a radial defect. The optical texture of these droplets is going to be very, very different. And what you're doing here is really sensing for the concentration of the surfactant, again, in a reversible manner. So the question becomes, can you use this for actual real biological molecules? The concentrations that you see here are pretty large. And here we got really lucky. Turns out that one of the colleagues that is collaborating with us in this process is Paul Bertix. And Paul Bertix is a biologist who's one of the world experts in endotoxin. Endotoxin is this molecule that you see over here that is abundant in the membranes of bacteria. And it is incredibly toxic. In fact, it is so toxic that all fluids that come into contact with the human body in the United States have to be tested for endotoxin. The saline solution that you inject in medicines has to be tested for endotoxin. Your eye drops, foods, everything has to be tested for endotoxin. This is a table that tells you what are the permissible levels of endotoxin. So for example, in a medical device or pharmaceutical manufacturing, stirred water for injection has to have less than 25 picograms per milliliter of endotoxin. That's nothing. More than that can be very dangerous. If you go to 200 picograms, it will kill you. The interesting thing is that the current test for endotoxin comes from the blood of the horseshoe crab. This crab species is actually only available in the United States in the East Coast, and the population is declining pretty rapidly because we use it to make endotoxin assays. Furthermore, the blood is pretty variable. Turns out that endotoxin actually serves as an anticoagulant for this blood. So the assay is actually based on this technology. So we'd like to replace that. So we thought about just trying it out with the liquid crystals. And sure enough, you see that in the absence of endotoxin, you have this basketball shape that I told you before. If you have 1 picogram per milliliter, you actually go from basketball to radial. And the optical signal changes dramatically. So you can definitely detect this transition using, what do you call these things for cells? The flow cytometer. All right, so there's ways of testing for this. Now the problem here is that we're still at the level of a picogram. We wanted to detect, microgram, we wanted to detect picograms. That's where the chemical engineering comes into place. So you can start designing the size of the shapes, the concentration of these particles, and so on and so forth, and actually design a system that gives you detection of endotoxin at levels of about 2 picograms per milliliter. So this is 10 times smaller or better than the current assays. You see that when the endotoxin is very small, the configuration is bipolar. The moment you have 2 picograms, most of the droplets become radial. So you have an on-off switch. You can really detect endotoxin. Now, what is really exciting about these results is that you do a back-of-the-envelope calculation, and you estimate how many endotoxin molecules are driving this transition. It is about 20 molecules per droplet. So just 20 molecules. That's nothing. 20 molecules do this thing. We don't understand how that works. It's a mystery. It's really unknown. We wish we did, because we could use it to design other sensors. So that's work for another time. All right, I need to thank my 2 partners in crime. Nick Cabot and Paul Neely have done most of the experimental work that you see here. Both of them are extraordinary colleagues, superb experimentalists. Without them, we couldn't do any of this work. And then I need to thank the students that you see over here. They've done all of the actual work. The ones in yellow have done the copolymers. The ones in green have done the liquid crystal work. Thank you very much for your attention.